everyone, welcome back to the Geo Academy YouTube channel. Today this is lecture 7, Geochemistry lecture 7. So today our topic is radioactive dating methods. So what are the different methods which we can date the rock? So I am very weak in dating, no girls date me. There are two types of isotopes like stable and unstable isotope. And in stable isotope mass fractionation will take place, and in unstable isotope radioactivity take place, like alpha, beta and gamma will emit. Now the examples we will deal with this only, because the radioactive dating method is mainly based on the radioactive process. Okay. The examples are rubidium, samarium, niobium, and there are different dating methods. Now rubidium converted to strontium and the half life is 48800 million years, and samarium converted to niobium and the half life is 10 to the power 12 years. Okay. Now and other are potassium argon and uranium, thorium, lead and carbon dating method. So we will learn all those things today. Carbon dating. So potassium argon, potassium converted to argon, the potassium 40 and the T half is 1190 million years. Uranium, thorium, uranium converted to lead, and the half life is 793 million year, and 92 205 and 82 207, and thorium converted to lead, and the 230 and the half life is 13500 million years. And carbon, nitrogen 714 plus X converted to carbon C14, this is proton plus proton P11. Okay. Yeah. Neutron, nitrogen, this is called thermal neutron cosmic rays. Thermal neutron cosmic rays. When nitrogen reacts with thermal neutron cosmic ray, it will convert it to carbon and one proton will be released. It does not generate daughter element. This is important and question asked from this. Nitrogen will not produce daughter element. Now first rubidium strontium method. So you know rubidium is a trace element less than 0.1%, okay, in the rock, having valency +1. It has the valency +1, which will replace K plus iron. Now how it will replace is the important question here. In K bearing minerals such as K feldspar, muscovite, biotite, antigold, and which are mostly concentrated in the crust. Okay. Now smaller strontium ion does not easily substitute for K plus. Smaller strontium ion, the diameter is so small and it cannot replace the K plus ion, and it will migrate into the minerals in the rock containing C2 plus ion, for which strontium easily substitute. Now for smaller strontium ion, it will replace the calcium 2 plus. Okay, because it easily substitute for the strontium. It will substitute the strontium very easily. Okay. So there are two basic concepts involved in rubidium strontium method. First concept is that original rock has same initial amount of rubidium 87, some initial ratio of strontium 87 by strontium 86, and some initial ratio of rubidium 87 by strontium 86. Okay, all those things will be present in the original rock when the rock is formed. So over time, since rubidium 87 is a radioactive element, and it will amount of rubidium 87 decreases and strontium 87 increases, because it is decreasing and it is increasing. Now rubidium is converted to strontium, so it will decrease and it will increase, which I have written here, increase by radioactive decay method. So that strontium 87 and by strontium 86 ratio will increase, and this ratio will increase. Strontium 87 by strontium 86 ratio will increase, and rubidium 87 by rubidium, this ratio will decrease simultaneously. Concept of rubidium strontium method is that initial amount of rubidium 87 varies from mineral to mineral. It is highest in potassium rich mineral, okay, and K like KLSI3 weight, okay, feldspar. In this type of mineral, the potassium rich mineral, the rubidium 87, and it is highest in the rubidium 87 is highest in the potassium bearing minerals. And the rate at which strontium 87 by strontium 86 ratio increases depends on individual mineral. So mineral to mineral it will vary, and it depend on which mineral we are taking in consideration. For example, in potassium rich mineral, that is rubidium rich mineral, strontium 87 by strontium 86 increases rapidly because it is a potassium rich mineral and there rubidium is high. So in potassium poor mineral, strontium 87 by strontium 86 increases slowly, okay. So in this case the increase is very slow. In potassium poor minerals, in potassium poor mineral, strontium 87 by strontium 86 increases slowly. For a mineral with no K or rubidium 87, the ratio of strontium 86 by strontium 87 by strontium 86 will not change, it will remain constant. Rubidium 87, strontium 87 and strontium 86 are determined. This is another topic, mass spectrometry, and we are not in the course, so we are not going into that. So basically rubidium, strontium and strontium 86, 87 and rubidium 87 are determined by mass spectrometry in the whole rock. For individual minerals, in the whole rock we can see for the individual mineral how much rubidium, how much strontium and how much strontium 86. Now rubidium 87 by strontium 86 and strontium 87 by strontium 86 ratios are calculated for it. We can calculate by using mass spectrometry method, and these are plotted on an strontium 87 by strontium 86 versus rubidium 87 by rubidium 86. Okay, and now we will plot the diagram. Now at the time of formation, now I am discussing another important point, and after that I will draw the diagram. At the time of formation, assuming no fractionation of strontium isotope, the strontium 87 by strontium 80 in each mineral and in the whole rock was a constant initial value, which varies from relatively high for Rb rich mineral and such as biotite K feldspar to 0 with no Rb rich minerals. This is the dating equation and this is the dating equation. Rubidium 87 rubidium 37 87 we converted to strontium 87 38 plus alpha particle. What is this alpha particle? This is He24. Okay. No, sorry, this is a electron with, I think, yeah, -1 0, yeah. Okay, so this is the dating equation. D is equal to D naught plus E plus P to the power lambda T minus 1. Here D is equal to strontium 87. D is equal to strontium 87. D naught is equal to strontium. D is equal to rubidium 87. Okay. Yeah. Oh. Now strontium 87 converted to strontium 87 0 naught plus rubidium 87 is equal to lambda T minus 1. This is the dating reaction, and dividing the above equation by constant strontium 86. So strontium 87 by strontium 86 is equal to strontium 87 by strontium 86 naught plus rubidium 87 by strontium 86 into e to the power lambda T minus 1. So in case rubidium converting to strontium, and here the value of lambda is 1.42 into 10 to the power minus 11, which is less than 0.1. Very less than 0.1. Now value of lambda T is less than 0.1. Now because of this, e to the power lambda T minus 1 will be approximately equal to lambda T, and then the above equation will be strontium 87 by the equation which I have written in the previous slide. Strontium 87 by strontium 86 is equal to strontium 87 by strontium 86 0. Rubidium 87 by strontium 86 into lambda T. So this is the equation. This is the equation which is equation useful to date the terrestrial rocks. Terrestrial rock means the rocks which are at the surface. We can date the rock by following this equation. Okay. Now, the significance of rubidium strontium method is that it is useful to date the Paleozoic rocks and Mesozoic rocks and rocks which are at the surface or at the crust, that is granite and gneiss, and it is very useful to date the lunar rocks. Lunar rocks means the rocks which are present at the moon. So now this is the end of the lecture. In the next class we will discuss potassium and argon method. Now thank you for your patience.